Hello guys, welcome to this video. In today's video, I want to talk about how you can check your FM front end, because I have seen there is not too many videos on YouTube about checking an FM front end. There are a lot of repair videos for older radios where they change the capacitors, stuff like this, but very rarely they show how you can check your FM front end. And we want to discuss this in the context of repairing an old radio, troubleshooting an old radio. And we want to look at some simple ways of testing for those guys of you which do not have a high-frequency laboratory like myself. I don't have a high-frequency laboratory, so we need to find some simple ways of checking and getting an idea of where we might have a problem. Now, here is the FM front end on my table, and I also have an FM IF amplifier, so I can check my FM front end acoustically and try to receive the signal. I will now give some power to the FM front end and the IF amplifier. Let's see if we can hear something. Yes, and since this FM front end works, we can receive a station. And here is the tuning knob. We can also change the tuning, okay? So for this FM front end, I know that it works. And now let's have a look at some schematics and maybe get a general idea how such an FM front end works, so that we can start looking for signs in our actual radio, whether there is some life in the FM front end or not. So here you can see the schematic of a Grundig radio, which I recently had on my bench. The FM front end that I have shown you a moment ago is not the exact, it's not the exact FM front end, but they all work in a quite similar way, and you will recognize the circuit because there's only very little variation. So you basically have always a 2-transistor design, and in some cases it is also a 3-transistor design. Then you have a separate oscillator. We will look into this in a moment more deeply. Okay, so what could be reasons to check an FM front end? And we start by looking at the schematic. So if you don't have any sound coming from your loudspeaker, so this is the audio amplifier here, and you don't have any sound coming to your speaker, you will have to check a little bit more carefully the whole circuit. I will usually start at the transformer, and then I start with and then I continue with the audio amplifier. So if you have power from the PSU and you have a working audio amplifier, then you should hear something if you put a signal in here. You could also use the phono jack, and then you should hear something. Now, if you use the phono jack, there is one thing that you have to take into consideration. There is some switching contacts, and they always are a little bit suspicious in such an old radio, because these contacts can make problems. So I would probably inject a signal here at the volume port, and then I would like to hear something here. And if you don't hear anything, then you need to check your audio amplifier, right? So the next stage that we are interested in is the IF amplifier. So we need the other page as well. So here is where the IF amplifier starts, and the IF amplifier, basically how it works, it's an amplifier for 2 frequencies. Here you have the AM front end, and then you will see these filter cans, which are basically switched in parallel. As you can see, this one is switched not parallel in series with the other filter cans, so that we have basically an IF amplifier for 2 frequencies. You have the AM IF, which is around 450, 468, something like this, kilohertz. And you have the FM IF, which is 10.7 megahertz. And this is basically how the whole IF amplifier works. And then here you have the demodulator, and it's also, one is for the AM section. This is usually the one with one diode. And then you have two diodes for the FM demodulator. And now what could happen in a radio like this? Maybe you have figured out your PSU works and also your audio amplifier works, and maybe you get some signal from the AM bands. So maybe you can receive some stations here, but your FM is dead silent, right? And that would be a situation where you would have a closer look into the FM front end. Now, as I said before, here you always have these switching contacts in these older radios, and they very often cause a lot of problems, and you need to clean them anyway. So this is kind of a prerequisite. But if this does not fix your problem, then you would definitely have to look into the FM front end. So what steps can you take to check if the FM front end works? The first thing is that you want to measure if there is any power at all. Usually there is one line which goes in, and this delivers the power to the FM front end. And you need to follow this line. So it goes via this resistor, and then there's a switch. So when we have AM reception, there will be no power going to the FM front end. But when we switch to FM, we will have power going to the FM front end. And then you simply follow this line. And then you can figure out the first point and probe there to see whether there's voltage, and then you follow the line and you probe again at the entrance of the FM front end, and you will need to see the power. If you don't see the power here, but you see it here, then it will get lost somewhere in between. It could be something as simple as a cable that got loose, could be a bad solder joint. Sometimes also it can be a burned resistor. So if you have something like a really bad short in here, you could have too much voltage drop across this resistor, and then you will not see any power here. Now these resistors, if you have a voltage dropping resistor in front of the FM front end, that is very nice, because then you can also measure the voltage drop across the resistor. And this gives you an indication. You can now use Ohm's law, the formula, and calculate how much current you drop, because you know the resistance and you know the voltage, and then you can calculate the current. And for a 2-transistor FM front end, you want to see something like in the range 5 milliamps, 6 milliamps could be okay. This one had very little, it had only 2.5 milliamps. So I would say a few milliamps, but certainly not 25, something like this would be off. And yeah, that would indicate for some problem in here. Now, in some schematics, like this one here, they also provide some voltages that you can measure on the transistor pins. So this would be the next thing to check. And sometimes you will also have to look somewhere inside of the explanation for the schematic, and they will have a separate section where they show all the voltages that you will find on the transistor pins. Okay, so the voltages on the transistor are the static bias points. So we need the bias points in order to have the transistors operate. Without these voltages, the transistors cannot function, and then you have found your problem if these voltages are not present. Or it could also be that some of these transistors are open or they are shorted, something like this. In that case, we will have to desolder them and check them individually if they work as transistors. Now, if these static voltages are there, what is the next step that you can do? And as I said, we don't have high frequency measuring equipment because many people don't have laboratory equipment like spectrum analyzers, stuff like this. So we will find we will need to find some simple ways of checking checking if we have a working FM frontend. And for this, let's get a piece of paper to first understand what an FM frontend does, what signals we get in, what signals we get out, and then we will develop some ideas how we can check those. So let's draw a simplified diagram how an FM frontend works and what it does. So at some place we have the antenna input. So this is supposed to be an antenna, right? And then usually you will see some sort of tank circuit consisting of a coil and tuning capacitor, like so. And then the signal will go into an amplifier stage, yeah? Amp, let's write short, amp. And we will have frequencies from about 88 to 108 megahertz, something like this. Okay, and then you will have a mixer. And then you will have an oscillator. And the oscillator will also have tuned circuit. Okay, and then at the output you will also see another tuned circuit. And this is your band filter. Now the mixer and the oscillator, these don't have to be two separate transistors. It can also be just one single transistor. In the example that I have shown you, the schematic, we had one transistor, and this is called self-oscillating mixer stage. So the mixer stage does the oscillation and the mixing. But from a perspective of functions, it is better to write 3 function blocks because we have 3 functions in an FM frontend. Now, what this does, I have already said the IF stage works with 10.7 megahertz. So we have to get 10.7 megahertz out of here. So that is clear. And we have an incoming signal with around 88 to 108. And so what we need to do, we have to have an oscillator signal that is 10.7 megahertz above the incoming frequency. And if we mix these two signals together, the incoming signal and the oscillator signal, we will get our IF. Okay, so the oscillator will run at around, let's take rough numbers, around 89 to 119, 119. So around about 89 to 119. And this already shows that we can use another radio receiver which we know is working in order to track the oscillator signal. Okay, so I will get a radio receiver and we will try this. So here I have the test receiver and we will be using the test receiver and we will try to receive the oscillator signal of our FM frontend. And as we have said, the oscillator frequency of the FM frontend will be 10.7 megahertz higher than the receiving frequency, than the input frequency. So we can only check frequencies above 98.7 megahertz, right? So what I did, I tried to find a spot above 100 megahertz. You can use frequencies of around 100 megahertz, but try to find a spot where there is no station. So I will switch this on now, and you will hear the typical noise that you hear in any FM receiver when you don't receive any station. So as you can see, I've tuned it to 100.6 megahertz. I'm not sure if you can hear my voice, so I have tuned it to 100.6 megahertz. And now I will not talk when I do the test. Basically, the tuning capacitor needs to be completely open to get the lowest frequency, and it needs to be completely closed to get the highest frequency. So I have to search on the lower end of the band at the 88 megahertz in order to receive the oscillator signal here. And you will notice that we will get a carrier. A carrier is simply a signal without modulation. You will hear that the noise on this test radio will go away, or it will at least diminish dramatically. So you are going to hear it. So I will give it a try. This is it. You can hear it. I will now rotate the knob very slowly, and there the carrier goes away. Now back to the other direction, and there you can hear the carrier. So this proves that our oscillator is working, which should not be too much of a surprise because we know that this FM Frontend works. But in case you cannot find your carrier, your oscillator signal, you know that you have a problem, because without the oscillator signal we cannot mix. And at the end of this video we are going to look with an oscilloscope at the 10.7 megahertz, and you are going to see we will not see a 10 megahertz signal if one of these components is not there. We need both components, because if you have an oscillator signal but no incoming signal, there's also nothing to mix, so there will be no 10.7 megahertz signal. And if you have an incoming signal but no oscillator signal, there's also nothing to mix. You need to have these both of these components in order to have a working FM Frontend. Now let's get the oscilloscope on the bench and have a look at what we can do with an oscilloscope. So guys, for the next measurement I have opened up the tuner module, and here you can see the layout a little bit better. So here basically we have the antenna input. This is the first stage, which is the amplifier stage, the first transistor. Now this is a very old FM Frontend. It uses germanium transistors, but that doesn't change anything. The silicon transistors work exactly the same way, only the voltages are reversed. And here you have the tank circuit for the input, and then here you have the second transistor, which is the oscillator and mixer. And here we have the tank circuit for the oscillator section, and this is your band filter. And here at this point, this is where we can take the signal out and go to our IF amplifier. Now for the next measurement I need to bring the scope in, and I need to zoom out a little bit. So for this measurement I have made myself a little coil. As you can see, it's maybe 5 windings that you can build using a pen, and then you make 5 turns. It's not really that important how many turns these are. And let's call this a sniffer coil. It gives us the opportunity to sniff in the circuit without directly touching it. So why do we want to do that? Well, these circuits, they do not produce a lot of power here, and it is very difficult if you use your ×10 probe. You will have very small signals which will not be visible on some oscilloscopes, and even for this test you need to have quite a bit of input sensitivity. So I'm here at at 2 millivolts. I don't know if you can read it. I will read it for you. So this is the maximum this scope can do. And with using this coil, the sniffer coil, we can basically go through the circuit and look for some signals without having the need to touch the circuit directly. And the reason is we add capacity, so we will detune the circuit. Now, if you look in the schematic of such an FM front end, there's very small capacity on the tuning condenser, like 2 to 12 picofarad. It's a variable condenser. And if you look at the specs of your oscilloscope probe, this will have something like 2 to 4 picofarad maybe. And so you will add this capacity, so it will detune the circuit. And in order to not disturb the circuit too much, we will simply not touch anything in the circuit. We only take the coil. So now what I will do is I will try to move the coil in the area of the oscillator coil, and then we should see some waveform on the oscilloscope. Let's give it a try. So as you can see, we are getting a signal here. And this is also a very simple test that you can do. And you don't even have to connect your oscilloscope to the circuit. You only use the coil and you will sense the oscillator signal here. I have set it to 10 nanoseconds, so it's a very short time, very high frequencies that we can see here on the display, and also a very high input sensitivity, 2 millivolts, and you have to set your probe to ×1, even if you use it in ×10 in most circumstances. Okay, now one thing I want to point out, this oscilloscope, I don't know if you can see it, it is specified at 50 megahertz. So how can I be, how am I be able to probe a signal that is higher than 50 megahertz? As we have discussed before here on the paper, the oscillator will have frequencies of around 98 megahertz to around 120 megahertz, which is way above 50 megahertz. Now keep in mind, what they specify is -3 dB points. So your oscilloscope very likely will not have a sharp cutoff at the upper end. Very likely it will fade out, you know. It will have less and less amplification on the input stage, and that means you cannot do measurements like these values that I'm reading here for voltage levels. These are not exact levels. But I can use this to do qualitative measurements, not quantitative. And at this point, we don't care how many millivolts of oscillator signal we have. We want to see that there is some oscillator signal, and we have clearly made that visible. So before you use your oscilloscope, I would suggest you try this with an FM front end, which you know that it works. So you can make sure you are able to make something visible on your oscilloscope, and then you can try it with the device under test, the one that you want to check out. So the last thing that I want to do with you is to measure the IF and make it visible on the oscilloscope. You can probably not see it very clearly. I have to move this a little bit. So I have connected my probe to the input of the IF amplifier, and what you are seeing on the screen is what an FM IF signal looks like. And I've put the frequency measurement here in the corner. It moves a bit around 10.8, 10.6, 11, so it's not quite stable, but we know it is around 10.7. And what you can see now, if I turn the tuning knob, that the signal will get smaller and smaller and finally fade away. So that means you can only see something on the IF if there is a signal that you can receive. I will now tune back. Let's see. this was the maximum, and then I will continue, and now it fades again until we find the next station on the band. Here is the next station, a pretty strong signal, as you can see. So this is a very clear indication as well that your FM Frontend works. Maybe we can find one more station in the band. Oh, there is one. This is a weaker signal. Here is one as well. Yeah, maybe these are the strongest ones that I can find. So keep in mind, we had this on the paper here. You need to have two conditions in order to get these 10.7 megahertz signal. The first condition is the oscillator signal. Without the oscillator, there will not be a mix down to 10.7. And you need to have an incoming signal as well. So without an incoming signal, there will not be a 10.7 megahertz IF frequency. So that's the last test that I wanted to show you, and you will pretty much be able to do this with an oscilloscope that has at least 10 or 15 megahertz of bandwidth. You don't need high bandwidth oscilloscope. So it's time for a quick wrap up. So when do you check your FM Frontend? I personally would check an FM Frontend if I have a radio which receives on the AM band, which has a working audio amplifier, but does not receive on the FM band. At this point, you are looking at the FM IF amplifier and the FM Frontend. Now, the IF amplifier is not very suspicious at this point because you have AM reception, and as I have shown you in the beginning of this video, in the schematic, that the IF amplifier is basically a two-frequency amplifier, and if it amplifies AM, then chances are it also amplifies FM. There could be a very rare error with a filter can, something like this. So it needs to be evaluated as well. But the next thing I would do is check the FM Frontend, which I have shown you in the video. The first thing I would do is check the band switches, because they are suspicious in older radios anyway, and if this doesn't solve your problem, you check the FM Frontend, which I have shown you in the video. How do we check the FM Frontend? So there's a number of steps that you can take even with very little measuring equipment. The first thing is you measure the voltages that go to your FM Frontend. The next thing to do is to measure the bias for the transistors. You have to see the voltages going to the transistors. If there is no bias, then the transistors cannot work. Then the next thing is you can check for oscillator signal with the second radio. And the next thing to do is to check for oscillator with a scope. I have shown you this with a coil, with a sniffer coil. And the last thing to do is to probe the output of your FM Frontend and see if you can get signal on the oscilloscope. This is also possible with oscilloscopes which have lower bandwidth. And one last thing that you can do, and this is the main reason I keep these spare parts here, you can also connect an external FM Frontend to your IF amplifier in the radio that you want to examine. And if this works, then it is very clear that the IF amplifier is not the problem. And also you can connect an external IF amplifier to an existing tuner module. And if this works, then your tuner is not the problem. So that's it for this video. I hope you liked this video. If you liked it, please come back anytime you want. There will be more videos like this. And bye for now.